Okay, so now we're going to be discussing about Karnaugh maps, or what's called K-maps. Previously, with truth tables, we've seen that they get a little too tedious, and we have to keep kind of finding cases where they are true, which cases they're false, and just in general, they get a little too tedious. So first, let me write any kind of function. Let's suppose that this was our function, AB C complement plus uh, DAB complemented plus, let's see, A or XOR B. I mean, notice that there's no way we can possibly just look at each case and say that this is going to be easy for us to understand. And actually, for this situation, I want to first deconstruct what XOR is and what this part means. Later on, we'll see with De Morgan's law why this is the result. A bar plus B bar plus A B bar plus A bar B. I mean, look at this. There's a lot of cases where it's true, where it's false, and so it gets a little too complicated. With K-maps, we can actually simplify this very quickly. So first, we have AB and CD, kind of constructed together like this. So we have 0, 0, 0, 1, 1, 0, 1, 1. Then we have 0, 0, 0, 1, 1, 0, 1, 1. We draw kind of a matrix table to represent each individual case. And anytime we see a multiple of 2, that means we're able to find a way to simplify it. Okay, so let us look at each part. A, B, and C. So anytime we see this part right here, we will write a 1 for it. So it seems that in this case, this is a valid 1, and this one's a valid 1. So we can pretty much stop there. Now, what about this one? We have D, A bar, and B bar. So that means that wherever there D is 1 and A is not true, then we're able to find it. So we have this one would be true, this one would be true. Then similarly, this one would be true, and this one would be true because of this. So we kind of look at this part. This is dA bar plus dB bar. dA bar means that when A is 0 and D is 1, there's an output there. Similarly, when B is 0 and D is 1, we can find an output there. Okay, so now what about this part? So A, B bar. So anytime A is true and B is false, then there is a 1. So we're able to find that there. Now, is there any other specific situation? This one right here. What about A bar B? So every time A is 0 and B is 1, then we are able to find it. And actually, it turns out that this entire row is true. So now we're able to see that the other ones are all zeros, and we're able to then now simplify. The easiest way for us to simplify, we find integer multiples of 2 that we can deconstruct. So in this case, this one is one that we can deconstruct. Like powers of 2 that we can deconstruct. So it's something like this. And finally, we have this. So we can deconstruct our function into something like this. Or actually, there's an even easier way for us to do it. Okay, so here's what we can do. So first, this and this can be combined. This can be combined. And that's it. So over here, we're looking at wherever there is no change for this. So it seems like with it that the only way there's no change for this is within these two. So we have a bar b plus a b bar. So that's our simplification. Then from over here, we have to check wherever there is no change. And in this case, we have just c bar d as our part that doesn't change. And then lastly, from over here, the only time that this doesn't change is when we have plus a bar cd. And that is how we're able to simplify our function. And actually, we can simplify this even further as a XOR b plus c bar d plus a bar cd. And if we really wanted to simplify this a little more, we can actually go one step further, factoring out d, and we get c plus c bar a bar. Or, sorry. So this becomes c a bar plus c bar. And that is our simplification. So hopefully you see that for K-maps, we're able to simplify the expression by constructing instead a matrix to list out the values, and we're finding wherever there is no changes. In the next video, we'll talk about a law in digital logic called De Morgan's law. Okay, thank you.